Hi, I'm Robert Toomey, and I work at the National Affairs Storms Laboratory in Norman, Oklahoma. This presentation is a very quick technical update to progress and changes to the RAPIO project in the last few months. RAPIO stands for Real-Time Algorithm, Parameter, and Input-Output. The name is the primary focus of the library. The main work in the last few months has been on data ingestibility. This is the I part of RAPIO, or input. With NetCDF reading, there has been some abstraction and improvement in the design. The first improvement has been reading of general NetCDF data files, attributes, and grids. Originally, we had hard-coded NetCDF data types. The upside of this was simplicity, but it's also limited our output ability when developing new algorithms. For example, with RAPIO, you can now add multiple bands of data to a RadialSet or lat-long grid and then read these new data fields in later algorithms. The second thing is general Grib2 reading ability, along with Grib2 extensions to the Woodsy index and FAM files. RAPIO allows for a pull system as well as a push system for new arriving data. Our original system had a push model for data that made reading Grib2 data difficult due to Grib2 being an n-field system. Basically, a Grib2 file is a collection of n uniquely compressed fields. By allowing a pull system design, we are able to quickly read uncompress only Grib2 fields that an algorithm is actually interested in. Some of the other minor I/O changes are being able to read and write HMET configuration flat files along with Woodsy style XML configuration files. There's also a non-FAM based directory watcher that's designed to pull data in situations where the more efficient FAM iNotify system cannot work, such as special network drives. Just as a couple of quick examples of the current algorithm API. Basically, RAPIO handles all basic data filtering and notification processing and passes data to a basic algorithm that you write. Here, for example, this is a current API code for getting a 2D Grib2 data grid from her Grib2 file. Basically, a template argument asks for the type of data you're checking for, and then if it's non-null, you then have a valid object to process. The goal of this API, of course, is to make it as simple as possible so that students can design and create algorithms as efficiently and quickly as possible. Those of you who have worked with the older Woods 2 algorithms know that with the API, it was very, very complicated just to get to the point of working with your data. So this tries to simplify that. This is one more example. This is showing requesting a RadialSet instead. So you can see it's the exact same type of code. Mostly all you need is just to change the template argument. So you're asking for a RadialSet. It's basically you tell it what the data that you expect. This allows you to handle various data types or future data types so they come without having to massively modify algorithms. Okay, let's talk about the changes to infrastructure. By far the largest infrastructure change has been the including of the Boost C++ library as a core library. So much of what we need to do is corresponding helper libraries within Boost, and this reduces the code we need to write and maintain. The only real downside to Boost I've seen so far is that the complexity can be a bit overwhelming for non-computer science background programmers. With this in mind, I did decide to keep a light adapter wrapper technique to simplify coding in the API. For example, we have a time class that wraps Boost in standard chrono, a logging class that wraps Boost logging, and string utilities that wrap Boost's various string algorithms. By doing this, it hides Boost from newbie student developers and also allows us to swap and prove things under the hood if, or when we decide to use better or different libraries later. For example, if we wanted to use AWS logging or even X-ray tracing calls embedded in our API, we can implement this without main MRMS developers having to back change their algorithms. The multi-array classes for RAM grids are very helpful in general for the array support for Grib2 and NetCDF reader classes. I originally wrote my own specialized array RAM class at first, but I found I was getting comparable speeds with the Boost multi-array. The Boost logging also can be very highly configured, which is nice. There's also the property tree classes, which are great because they basically read XML and write XML for free, and you can even do JSON read and write as well. And there's crash handling, which is also decent for like core dumping or stack tracing. So let's look at the action list. Many of the things planned last time are mostly completed, although a few are still left. The first thing being the heartbeat syncability. Basically, the idea around this is to enhance the archive real-time mode to increase the number of ways that an algorithm can actually be ran. I think this will be good to have, especially if we move towards running algorithms in auto-scaling cloud environments. The general projection ability is going to be necessary for advanced output of data at some point. Currently, we write only netcdf output in an assumed projection system, the original Woods2 formats that we had. Data ingest for Grib2, for example, can have very many different projection systems, and we need the API for seamlessly moving between these projection systems. And then is the precision scaling is something I also still want to experiment with, since I think if we got this to work well, we could drop our I/O quite a bit. I think with the new stuff, the focus is still on I/O. This is currently our biggest issue with all data processing and algorithms. FAM alternatives are one possible way to drop our I/O requirements. Instead of file notification, we could use something like Amazon SNS with fan out to SQS, Elasticache, or even DynamoDB for metadata. We could even experiment with Kinesis, though I think this would be the most technically challenging option. HDF5 general readability might be nice. If Michael's listening, maybe he could help with that. And I feel like we're very close to now to be able to include this in the MRMS build. This will allow Woods2 and MRMS algorithms to use this library for new streamlined algorithm development. So last thing, of course, is where to get it or where the code's at. Currently, the code is on GitHub at the following address, the http github.com RAPIO. And soon, hopefully, I'll have a flag in MRMS Builder that will allow to be built into the build and used.